welcome to CEC lectures. Myself Dr. Priti Jagwani from Department of Computer Science, Arabic College, University of Delhi. So, in my previous lecture we talked about network layer addressing and we looked into the format or the structure of IPv4 addressing, which is mostly prevalent in kind of two forms. One is the binary notation, another one is the dotted decimal notation, and here is a figure which we have already looked into showing the two decimal notations, showing the two IPv4 address notations, dotted decimal notation and the binary notation. Moving forward, we kind of today we are going to discuss about the schemes, representation schemes of this IPv4 addresses, and this representation scheme talks about the two things. One is the classful addressing, another one is the classless addressing. So, basically two types of IPv4 addressing schemes we are going to look into. One is the class 4 addressing, another one is the classless addressing. So, when we talk about classful addressing, since the inception of this IPv4 addressing schemes, it is using the or it has we can say it had used the concept of classes. But nowadays this scheme, let me tell you, is becoming obsolete, which shows the rationale or which paves the path for using the classless addressing. So, since inception the concept of classful addressing have been used, but nowadays this is kind of becoming obsolete, and now we have moved on to the classless addressing. But this, it is very important to understand about this classful addressing. So, this whole address space which I was talking about, that it is more than 4 billion address spaces, but theoretically we cannot allot all these addresses, all these 4 billion addresses to different devices, because there are so many restrictions. So, this classful addressing is going to give us an idea about those restrictions also. So, this scheme says that address space is divided into 5 classes: A, B, C, D and E. Each class is going to occupy some part of the address space, and we can find the class of an address when given the address in binary notation or maybe in the dotted decimal notation. If the address is being represented in binary notation, the first few bits can immediately tells us the class of the address. If it is being given in decimal dotted notation, the first kind of byte, or we can say the first byte, is going to define the class, which is we can say just before the first dot. So, here if we see binary notation or if we see dotted decimal notation, so you can say class A, if it is in the binary notation, is going to, if the first byte is 0, then the address is going to belong to class A. If it is class B, then the starting will be 1 0. If it is class C, then it is going to be 1 1 0. For class D it is 1 1 0, and for class E it is going to be 1 1 then 1 1. Now, if we look into the dotted decimal notation, anything which is starting from 0 to 127 represents class A, 128 to 191 represents class B, while class C is represented by 192 to 223, 224 to 239 is representing class D, and class E is being represented by 240 to 255. Now, all these 5 different classes A, B, C, D, E have their own kind of, we can say address space, or have their own scope. We will look into this. Now here the class A addresses basically designed for large organizations with a large number of attached hosts or the routers which are attached to them. Class B, if we look into, they are designed for mid-sized organizations with nearly tens of thousands of hosts or routers attached, and class C address were designed for kind of a small organization with a small number of attached host or routers. So here how many number of blocks or we can say devices can be connected. So class A, so 2 to the power 7, that is equals to 128 blocks will be there, then whatever is left will become the block size. Now in the rightmost column, the application is also being kind of displayed. So whether it is going to be used for the unicast application or it is going to be used for multicast applications, that we will also see soon. Then class B, if we talk about, so again 2 to the power 14, which is equals to 16,384 number of blocks used for unicast addressing. Then class C, which is 2 to the power 21, which comes as 2097 hundreds we can say, is also kind of used for unicast applications. So class A is going to represent large organizations with huge number of hosts, tens of thousands of hosts are there. Class B will be appropriate. Class C is used for small organizations. But now what about class D and E, where only the number of block is 1, and if you can see in the right side, which is going to show the application, so it is multicast and reserved. So class D is for multicasting and class E is for reserved application. So if we talk about how this classful addressing works, a block A in class A address is too large for almost any organization. So block size, if you can see, is 16777216. This is a huge a size we can say. So this is too large for almost any organization. That means if we are going to allot class A to a particular organization, most of the addresses in this class will be wasted and were not used. If we talk about the class B, in which the total number of blocks is 2 to the power 14, where the block size is 65,536, that too is actually a large number, probably we can say too large for many of the organizations that received a class B block. Class C, if we talk about, that is 2 to the power 21, total number of blocks is 2 to the power 21 and the block size is 256. We can say probably too small for many organizations. So here are these kind of we can say these restrictions, or we can say the limitations. Class D address is basically designed for multicasting, and each address in this class is used to define one group of host on the internet. The internet authorities initially they we can say their assumption was wrong. They wrongly predicted that a need for 268, 435, 456 groups, this much of group is actually not required. So this has never happened and many of the addresses are wasted here in this class D address also. So if you can see, class C address is kind of too small, wastage in class A, wastage in class B also, and wastage in class D as well. Lastly, if we talk about the class E, these addresses were reserved for future use and only a few of them were used, resulting in another wastage of address. So, we looked into the limitations of this classful addressing, in which so many address space, so many addresses in each sub address space have been wasted, and because of this that 4 billion addresses have been kind of, we can say, just they were available theoretically. Practically, because of these restrictions of these classful addressing, these 4 billion addresses were never used at a particular point of time. With also in classful addressing, an IP address is also divided into this net ID and host ID, and this net ID and host ID are parts, we can say, of varying lengths within that IP address depending upon the class of address. So, if we look into how this is going to happen, so here we have a class, then there is a kind of address which is written obviously in the binary notation. We have dotted decimal notation corresponding to that also, and then CIDR corresponding to it, which is /8. Then B is having kind of 2 bytes. So, taking this figure in mind, let us try to understand what is this net ID and what is this your host ID. So, in this figure we have looked onto some of the net IDs and some of the host IDs which are varying length. So, here you can say, here you can see that some parts are shown in your colored, and some part are shown in normal black thing, and this itself carries a meaning. So, the net ID here is shown in color, host ID is given in black and white. Note that the concept does not apply to class D and E, and hence only the 3 kind of classes A, B, C are there. D class is there for multicasting as we have seen earlier, and E is also the reserved. So, we are going to look into the concept of net ID and host ID only for the class A, B and C. In class A, the first byte, 1 byte defines the net ID, 3 bytes define the host ID, and hence only 1 is colored, if you can see. In class B, the 2 are going to define the net ID and the next 2 are going to define the host ID, while in class 3, the initial 3 bytes define the net ID and 1 byte defines the host ID. So, here is the concept of net IDs and host IDs. Now, network address, if we talk about, we have seen that they can be unicast, multicast, broadcast or anycast. Now, here is the time to look into all these terms in detail. So, when a device has multiple paths to reach a destination, it is going to select one path by preferring it over others, and this selection process is termed as routing, done by router, the special network devices or the special internetwork devices, routers, or it can be done with the help of software process. Generally, this task belongs to routers. The software based routers have some limited functionality and limited scope as well. Now, when we look into the routing thing, a router is always configured with some kind of default route, where this default route is going to tell the router that on which path you need to forward a packet if there is no route found for a specific destination. In case there are multiple paths existing to reach the same destination, router can make the decision for the best route to be opted for on the basis of some information. Now, which information I am talking about? It could be hop count, it could be bandwidth, it could be some different metric, or the prefix length, or how much delay is there on a particular route. So, depending on these information, or we can say by banking upon on these hop count, bandwidth, metrics, prefix length and delay, or any one of these information can be a parameter to look for the kind of we can say the best way to reach out onto the destination if there are multiple paths existing to reach that particular destination. Now, unicast routing, if we talk about, most of the data traffic on the internet is unicast traffic. Basically, it is sent with a specific destination. So, routing the unicast data over the internet is, the common term used for this is unicast routing. It is the simplest form because destination is already known. In any cast routing, the destination is kind of the nearest one, not known. Hence, as the destination is already known, what will be the job of router here? The router has to look up to the routing table and forward the packet to the next hop. Now, if you can see here in this figure, we have a source and a destination, and with the help of arrows one particular path is being shown, which is shown as the straight path here in the on the screen. So, from the source it goes to the router 1, we can say, then the next hop, and then the next hop, finally to the destination. So, just by looking into the header field, that for which particular destination it is being kind of destined for, it is being the data or the packet or the traffic, we can say, is being forwarded to the destination, and this is what your unicast routing is. Moving further, if we say broadcast routing, so by default I have already told you in my previous lecture that the broadcast packets are not routed and forwarded by the routers on any network. Routers are going to create broadcast domains, but it can be configured to forward broadcast in some of these special cases, but generally routers create broadcast domains, and by default they are not kind of packets are not routed and forwarded by the routers on any network if it is the case of broadcast routing. So, broadcast message is destined to all network devices, and this can be done with the help of two algorithms, we can say. Now, what are these algorithms? Let us look, we will be looking into. A router creates a data packet and then sends it to each host one by one. In this case, the router creates multiple copies of the single data packet with different destination address. So, the content is same, but the address is destination address is different, and all the packets are sent as unicast packets, but because they are sent to all, it simulates as if the router is broadcasting. So, for example, there are 4 devices, so same packet or the same data will go to 1, the next copy will go to 2, the next copy will go to 3, and the last copy will go to 4, and all the 4 copies are having different destinations as 1, 2, 3, 4. So, actually it is being unicast, but because these packets are sent to all the devices, it simulates that if router is broadcasting. That is kind of one way of doing broadcasting, but this method consumes a lot of bandwidth, and the router must be aware of the destination address of each of the node. The second algorithm or the second way for the broadcasting is when the router receives a packet which is to be broadcasted, it simply floods those packets out of all interfaces, and all the routers are configured in the similar way. So, whenever the router receives a packet, it simply floods that packet onto the all we can say interfaces. Here is a figure which shows the broadcasting thing. So, it starts from the source on coming to the first hop. After the first hop, it is being kind of we can say broadcast or sent to all other availables, and hence all the routers on the kind of on the way are going to do it in the similar fashion. The moment they are going to kind of receive it, they are going to send it on to all other links, and finally your packet or your data is going to receive is going to reach onto its the designated destination, or definitely it is going to kind of reach out to that one. Moving further, so this was your unicast, or we can say broadcast, and we have seen two methods of broadcasting also. Now this method is easy on a router's chip, because but may cause the problem of duplicate packets received from peer routers. Now in order to kind of, we can say, detect and discard duplicates, we need to use a technique which is known as reverse path forwarding, in which the router knows in advance about its predecessor from where it should receive the broadcast. So there are problems, and hence there are solution also, but this method is easy but may cause some problems of we can say duplicacy. Moving further, if we look into after this unicast and broadcast, we have one more kind of way which is multicast. So multicast basically can be said as an special case of broadcast routing with very different challenges, very different significant differences also. In broadcast routing, packets are sent to all nodes even if they do not want it, but in multicast routing the data is sent to only the nodes who all those nodes which wants it, which wants to receive the packet. So not to all, but to the selected ones. This is what the basic fundamental behind multicast routing is. Now here in this figure you can see the multicast routing. Here there are kind of two destinations, and hence the source is forwarding the packets or the data or the traffic to the designated destinations, which are obviously more than one. So it is not unicasting, it is not sending it to the all, and hence it is not broadcasting, it is sending it to the kind of designated ones, and that is why it is the multicasting thing. But the router must know that there are the nodes who wish to receive this multicast packet or these streams, then only it is going to forward to those nodes. Multicast routing works spanning 3 protocols in order to avoid looping. Then multicast routing also uses reverse path forwarding technique to detect and discard duplicates and loops, which was also kind of used by the previous technique of broadcasting. Moving further, we are left with anycast routing. Anycast packet forwarding is a mechanism where multiple hosts can have same logical address, and this is the mechanism which in which we can say we have talked about that the network address is going to be unique at same point of time, but may have the duplicacy at different times, different durations. So when a packet is destined to this particular or any particular logical address and it is received, it is sent to the host which is nearest in the routing topology. So here if you can see, we have a DNS server from from source the traffic is being originated, and there are 3 destinations. So we can say the 3 different anycast destinations having same logical address, but it is being sent to only the nearest one, and this is what the fundamental way of doing our anycast routing. This is done with the help of DNS server, and hence the DNS server is being shown. Whenever an anycast packet is received, it is inquired with DNS that where to kind of send it, and DNS provides the IP address which is the nearest IP configured on it, and hence your anycast packet is sent. Let me summarize the lecture. In this we looked into the different schemes of different schemes of IPv4 addressing, and then we also looked into different mechanism of network addressing, which are unicast, multicast, broadcast and anycast. We also looked into these addressing schemes in a detail, and we try to understand the nuances also. Here is a list of references which is being used for the preparation of lecture. I will see you in the next one. Till then, take care. Goodbye.